Okay, welcome back to our practice. The skills required to be able to understand the concept for this practice are to be able to find the area of a square and its side length, also known as the square root. Here are some problems to help us make sure we can do that. If you're having trouble with any of these, go back to the previous video for reference. All right, let's check. You can either pause this and try it yourself, or you can check in your head. Let's do that now. All right, so remember that the area of the square means how many of those little smaller square tiles are inside. For this particular example, how many are inside? And it should be 36. How many little squares are inside this one? If the side length is 9, it should be 81. How many little squares inside this one? It should be 17 times 17. So hopefully you recognize that as 289. How many little squares inside of this one? It is 10 times 10, or 100. And for this type of square, remember that we're going to square the numerator and denominator. So what's the numerator square? It is 4. And denominator square is 49. So 4 over 49. That should be the area of this square. And remember that this is one of those special examples. If you don't understand it, refer to the previous video. But the square root of 5 times the square root of 5 is the same as square root of 5 squared, which simply becomes 5. The area is 5, all right? So hopefully you remember that this is a 5. Another notation for this is if the square is inside the square root, like this, that's still a 5. Okay, so that's the squares, and let's check the square roots. Now this is reversing the thing from the previous part. If there are 4 little squares inside, what was the side length, or what's the square root? The square root is 2. For the area 144, what is the square root? It is 12. If you're thinking 12 times 12 instead of square root, that's also okay. If the area is 16, what's the side length? It is 4. If the area is 225, the square root is 15. Hopefully you're okay with me interchanging the name of the side length from square root to side length, as I will do here. What's the area? If the area is 17, what is the side length? Now let's look at the previous ones. They all happen to be, the areas all happen to be perfect square numbers. Therefore, we can represent a side length as a perfect integer. But another way of representing the square root of, another way of representing the area of the square root of 16 as 4 is also the square root of 16. Don't forget that. That's why I kept saying that. I stumbled with my words there. It's all right. Let's keep moving. So therefore, that implies that for a non-perfect square root, like 17 number, then the only alternative here is to say square root of 17. We cannot rewrite this side length as a perfect square integer. It's some number between 4 and 5. And that's all right. This is the way we're going to do it and moving forward. Now, this fraction has both perfect square root numbers. So therefore, the side length is going to have a fraction with both integer numbers. The square root, let's do it in parts. The square root of the denominator, I guess since I said that, let's start with the denominator. Square root of 49 is 7. And the square root of the numerator is 10. All right, excuse me if we went a little too slow there, but this is required in order to understand what we're going to do today. So if you had any trouble with that, please refer to the previous video. Now, let's go away from the pictures, and I'm going to ask you the question. Think about it like this. What was squared to obtain these numbers down here? In other words, what quantity or what number or something squared equals 9, something squared equals 36, something squared equals 4, something squared equals 15, and so on with these numbers. So let's think of at least one number, right? Because if you remember the previous video, there's actually 2 for each one of these. So if you forgot that, or if you didn't keep that in mind, I'll give you a little more time to think as to what that could be for these 4 possibly. All right. All right. I hope that you don't need any more time. Let's check. Hopefully that you thought one of the numbers that was squared was a 3. 3 times 3 is 9. But what was the other possibility? Not a positive number, but hopefully you were thinking of its negative square root, the negative version of the square root. The square root of 9 is 3, but there's also a negative version of that. So here we were thinking 6, and I'm going to say 3 or negative 3. What's the other option for squaring to get a 36? It's going to be either a 6 or a negative 6. What 2 numbers were squared to get a 4? Those 2 are either a 2 or a negative 2. And remember that those were perfect square numbers. We saw that same thing going on here. So another way of rewriting that is that here we can say this is the square root of 36 or the negative square root of 36. Whoops. This one right here, we could have said square root of 9 or the negative square root of 9. Those are both equivalent. These two are the same numbers represented in different notation. So because 15 is not a perfect square integer like the previous three, the only way that we can write that one is not as an integer. The only option here is square root of 15 or the negative version of that. That's the only way we can represent that one. So always look at that yourself. Is this number a perfect square or not? And if that's the case, then yeah, I'm just going to skip the square root of 144 and negative square root of 144 part and write 12 or negative 12. Hopefully you recognize that as the square root of 144. And I'm going to ask myself the same question. Are both of these numbers, first of all, is the numerator a perfect square? Yes. Is the denominator a perfect square? Yes. So therefore we can write fractions with integers. So therefore this is a 2 over 7 or its negative version, negative 2 over 7. I think that was the same one from the last problem. I usually do those things on purpose. Look at that, 4 over 49. There it is, just so we can make those connections. And I want you to point something out here. All of these represent the area of a square. 9 represents the area of a square. 144 represents the area of a square. However, there's only one side length, only 12, not negative 12. But to keep that in mind, however, because can the area of a square be negative 4? And look at the picture, all of the squares were not negative. So what we said about this is that there's no real numbers solution, all right? And the way I'm going to start writing that, I'm going to say no. At first, most mathematicians write no solution, but that develops a bad habit. I'm going to say no real solution. And what that means for us in this course, it means no real number, all right? So no real number. There will be solutions to these in the future. In our practice, future practice, all right? There's been solutions to these in the past, long time ago. And again, recognize 37 as not a non-perfect square number. So therefore, only possibility to write this as is the square root of 37 or the negative square root of 37. If you understand these ideas, then we're definitely ready for the next part. And we're pretty much already doing something advanced in mathematics. And I'm going to gradually develop that here, starting with number 3. So look, we've already done this in words. It's said before, what was squared to obtain these numbers down here? And number 3 is asking the same thing. It's saying something squared equals 9. However, we're introducing symbols with it, basic symbols. My favorite symbol is something. Something squared equals 36. Something squared equals 196. Something squared equals 21, and so on. We're going to be able to write that because we've already done the same type of questions up there. And notice how I chose these 3, 9, 36, and 144. They're the same from before for your reference. So you can see nothing different is happening. What was squared to get a 3? Remember, there are 2 possible values. We're going to say the something equals a 3 or the something equals a negative 3. Very similar to what we did on the problem above. Something squared equals a 36. What are the 2 possibilities? Something was either a 6, and the other possibility for that something is a negative 6. 196, is that a perfect square integer or not? And it turns out it is. So there are 2 possible numbers we can square to get a 196. One of them is a 14. That's the first something. And the second something is a negative version of that. All right. So always looking for that. Is 21 a perfect square root number? And it turns out that it's not integer. So therefore, we're going to say the something either a square root of that number, 120, just 21, or the other possibility is that it was a negative square root of 21. And at this point, I'm getting tired of writing this a little two times every time, and you probably will get tired of doing this at some point. So I'm going to introduce a quick notation down here, just so you can see how I'm going to write this in the future. And instead of writing 2 parentheses 2 times, what mathematicians found as a convenient notation was to say the something, our solution is going to be either a positive. If you have seen that symbol before, then you're already familiar with it, or a negative square root of 21. This in green down here is the same as this one. So these two are equivalent. So this is just more convenient, which it's going to allow us to say things like something equals a positive or negative 14 to signify that there's two possible solutions here, all right? So moving on, we will use that notation now. And again, look at the number, perfect square or not perfect square. And turns out it is. So something, what's our new notation going to be here? Plus or minus 12. And there it is. We're done with this one. That one's done. Something squared equals a positive fraction with both perfect square numerator and denominator. So we can conveniently say something equals a positive or negative. What's the square root of the numerator? That one's very easy. It's just the 1. What's the square root of the denominator? It is 5. So positive or negative 1 over 5. Those are the two possible solutions. Hopefully you're getting the hang of this. And another thing to look out for, first of all, before you ask yourself, is this a perfect square or not? You should be definitely looking at this negative. Is it positive or negative? Because positive numbers we can solve, but not these negative number ones. The area cannot be negative. So therefore, we're going to say there's no real solution here. No real solution. All right, common mistake that I've seen before is that some people may still write something equals a positive or a negative 3. Always keep in mind that negative represents an area. An area cannot be negative, all right? So this one is positive. The next one, we're okay with that. And it's not a perfect square integer, but we can still solve it. We can say positive or negative square root of that number is our something. And this problem is done. That's simple. There was no real work that needed to be shown. We just know that there's two possible numbers to square a 36 or a 144. All right, so if you're feeling good up to here, then we're ready to go to 3B. 3B is going to be pretty much the same of what we just did, but with a more fancy advanced algebraic notation. This is the type of notation that we see in algebra, but I want you to read it the same. The first 3A, we were reading it as something squared equals 9, something squared equals 36, something squared equals 196, something squared equals 80. We will do the same thing here. Rather than thinking x squared, I will still think something squared equals 9. Rather than thinking p squared equals negative 8, I will still think something squared equals negative 8 because that's more intuitive, all right? All right, so let's think about that. And again, hopefully you notice this has been done in the previous problem. This one has too, and maybe even this one. Just to allow us to make those connections in a much easier way. And I want to continue to use my notation. So something equals, how many possible values could we square to get a 9? There are 2, a positive and a negative 3. That's it. Look how simple we're able to solve, or how quickly and efficiently we're able to solve these. Something squared equals a 36. That something better be a positive or negative 6, as we've done this one many times already. And then I want to show you one that is very easy, but it can be easily confusing. Something squared equals 1. How many possible values? Just like before, a positive or a negative 1. So hopefully you got that one, didn't get confused with it. And I still read this as something equals positive and negative 1. How many values can we square to get a 144? There are 2. So the something now k, notice how I'm still not calling it k, I'm still calling it the something, is still a positive or a negative 12. All right, so I don't want us to think n squared equals, I want us to think something squared equals this fraction. All right, something squared equals the fraction. And the fraction is positive, so we have 2 possible answers, positive or negative. Now look at the numerator. Is that a perfect square or not? It is not. So what's our notation that we can use? Square root. We can say square root of 27. But what do you notice about the denominator, the 16? Is that one a perfect square? It is. So we can either write it as square root of 26 over square root of 16, but I like simplifying. So we're just going to say square root of 26 over 4. The square root of 16 is 4, all right? So that's the way I would write that one first. Like just go straight to the answers, all right? That's okay. And so what I'm trying to say is if some of you thought of writing as plus or minus the square root of 26 over the square root of 16, that's great because that also equals this. Don't want to go too into detail with this lesson today, but those are 3 equivalent ones if you were thinking about them. All right, and always think something squared. Can something squared ever be a negative? We already know that's not the case. What do we say in those instances? We say that there is Oh, I don't know why I'm doing that. Let's just reset. Give you a little more thinking time though, it's all right. So we say that there is no real solution. And if you're still wondering what that means, no real numbers can satisfy this equation. No real solution. All right, hopefully we didn't spend too much time on this, and let's go to a little bit more advanced. I think this is our last part, but again, we're gonna start with some simple, more intuitive symbols like something square, my favorite, and then end up with something more abstract, all right? And hopefully you feel comfortable so far. All right, so again, always think of this as something square equals 121. How many different numbers can we square to get that? It is 2, a positive and a negative 11, all right? If I'm going too fast at this point, pause the video, try them for yourself, or check them in your head. And either way, let's do that now. What's the next one? Something square equals 64. There's only 2 possibilities, and positive and negative 8 is what we can get here. Something square equals 0. There's only 1 possibility there, but it wouldn't be wrong. So look, something can only be 0, but it wouldn't be wrong technically if you say plus or minus 0. Even though 0 is neither positive or negative, it's like you're adding 0 and subtracting zeros, which is okay mathematically, still works. All right, but I would go on these and just box that one, although the plus or minus 0 is not wrong. Okay, great. So look, we did something square equals 121, and we're going to do it again. Something square equals 64, and we're going to do it again. But like I said, we're going to do something more advanced with these. So something more advanced will look something like, oh, well, it's fine. Let's keep this green color. Suppose that instead of something square, it's not just something, it's the something inside, or the something is x plus 5. Something square equals 64, where the something is x minus 3. And something square equals 0, where the something is x plus 6. However, I don't want you to think and read this question as x plus 5 quantity square equals 121, or x plus 5 squared. We will still focus on something squared equals 121. The next one we will still think about as something squared equals 64. And the last one, something squared equals 0. That's what we should train our eyes to look at first. Not the x plus 5, not the x minus 3, but the something squared. That's what we've been emphasizing that for so long. And I want you to think the same. How many possible values could the something be to get a 121 squared? It's either a positive or a negative 11. We did that before. But the something inside is x plus 5. That means that we have one more step to undo here. And just like we did in linear equations back in algebra, think of it like x plus 5 is equal to some number. How do we undo the plus 5? We're going to subtract 5 on both sides. So we're going to write this one as x equals a negative 5, add 11, but also subtract 11. So I want you to think that. If you haven't seen this before, then I'll write it twice for you down here. This means x equals a negative 5 plus 11, and it means x equals negative 5 minus 11. I won't be simplifying these right now, because if you can get this far, you pretty much solved the problem. This should take less than 2 seconds or less than 5 seconds from here. All right, check that on your own. I will be checking that in future videos, not at this point. All right, so same thing here. I want you to think of something squared equals 64. But how many numbers can we square to get a 64? We have 2, positive and negative 8. And the something inside is a x minus 3. So that gives us one further step to undo this negative 3. How do we undo subtracting 3? By adding 3 to both sides. That will give us on the left side just x. And on the right side, we get a 3 plus or minus 8. There's no need to write the plus 3 here. Just know that it's positive. It's implied by not writing a negative. And this is as far as I'm going to go for this video. I'm going to box that as my 2 solutions represented, not simplified. And then how many things can we square to get a 0? That one is just one number. X plus 6 equals 0. And that means that x equals negative 6. All right. But remember that if for any reason you wrote plus or minus 0, I want you to see that it's still mathematically correct. Plus or minus 0, because then the answer would become negative 6 plus or minus 0, which again turns out to be that. Let me make a better arrow here so you understand that symbol. There we go. Okay, that's it for these we've done these already. This is like the next step, right? Just to make sure we got this, I wrote a few more, maybe 4 more that you can either pause and try right now, check in your head, but whatever method you chose, let's do that next, all right? And I'm gonna, hopefully you notice, I stopped writing it in color, just so you see this is what it will look like in the future, all right? So let's start with the top. Again, don't think of it as x minus 7 squared. It is something squared. Something squared equals 43. How many somethings can we square to get a 43? It is 2 of them, positive and negative. Now look at 43. Is that a perfect square integer or not? It is not, so we will write plus or minus the square root of 43. And then the something is x minus 7. Then carry it over at this point, x minus 7. And the last thing we need to undo is x minus 7, so we can isolate that x term. We have x equals, what's the opposite of subtracting 7? Adding 7. So we have a 7 plus or minus the square root of 43. And now we're doing some that are pretty advanced. Look at that. Those don't look too easy, right? But you're doing something complex already. Something square equals 39. Is 39 a perfect square integer? It is not. So therefore, we will say the something equals a positive or negative square root of 39. What's the something inside? The something is x plus 8 term, x plus 8. And now we need to undo that. It's pretty simple. How do you undo adding 8? By subtracting it. So the two solutions can be represented as x equals negative 8 plus or minus the square root of 39. All right. The decimal answers can be found using a calculator, but I won't be using a lot of time to do that or any. All right, something square. This one should be pretty simple. Something square equals negative 1. What do we know about, can we square a number and get a negative? Not in the real world system. So we're going to say no real solution. No real solutions. Okay, great. And then last one, I wanted to do one involving fractions just so you can see what you're able to do up to this point. Something square equals some fraction. And the nice thing about these fractions is both numerator and denominator are perfect squares. So I will use the integer format of the square roots. So I will say something, still a positive or a negative. What's the square root of the 49? The square root of the numerator is 7. What's the square root of the 4 or the denominator? That is a 2. And the something inside, what's the something inside? X plus 5 over 2 or x plus 5 halves. However you prefer to read that. And just like the other problems from before, don't overthink this. We're not doing fractions at this point. Yeah, think of 5 over 2 as a number. How do we undo a positive 5 over 2? By subtracting it. We're going to subtract 5 over 2 on both sides. On the left side, we remain with an x. And then we have to add and subtract this fraction from that. So negative 5 over 2 plus or minus the 7 halves, or 7 over 2. And this is as far as I'm going to go in this video, but I chose these to be same integers so that if you want to take some time and add these, those will simplify very nicely. All right, we have reached the end of this practice. I hope that you feel okay and feel very gaining confidence and comfortability solving your first type of quadratic equations. Believe it or not, this is an important skill for future lessons. All right, I hope to see you in our next practice. Have a good rest of your day.